Hi, everybody. Thanks for coming to this Taste of Modeling workshop. My name is Eric Robinson, and I've been teaching physics since 2012. I got into teaching physics because I was unsatisfied with my own high school physics education experience. So I went to college with the intent of seeing if there was a better way. I got into teaching, and at the start of my career, I was kind of doing the same thing a lot of other teachers do, where they basically mimic their best teachers. And it was effective. It only took me so far. And then around the holiday times, 2016, going into 2017, I was getting ready to teach energy after the break. And even though every science teacher knows how devastatingly important energy concepts are, I always got to the end of that unit and my kids, they just didn't get it. They could solve the problems, but when it came to having conversations with them about what energy meant, what it is, how to think about it, where it applies, I was really unsatisfied with the outcomes that I was getting from my own approach. And so after doing some like targeted Googling of asking the internet, like what is the most effective way to teach energy concepts? What are labs that are really good at teaching energy ideas? That's kind of what caused me to stumble into the modeling community. I had found a modeling blog that talked about a very neat lab that I still do to today. And actually, now at my department, all of our teachers do a different version of it. The what I call it is energy station rotation, where to introduce the idea of energy, the students visit 4 different stations that are designed to explore energy in different ways. For myself, one setup has Hot Wheels, one setup has magnets, one setup has a hand crank generator connected to a light bulb. And without talking about what energy is, without giving them any direction, we just have the kids visit all 4 and then have some guided discussion about what energy is. Um, After trying that one lab on my own in my classroom and then seeing how effective the outcome was for the students, that's when I attended my first summer modeling workshop. Um, and ever since then, it's like transformed my practice. And now all of my lessons are modeled top to bottom. A lot of people are here attending this webinar, which thank you. Thanks for coming out. Thanks for taking the Monday of your Thanksgiving break to listen to a modeling workshop. Um, if you ask 100 different modelers what modeling is, you get 100 different answers. The description of modeling that I'm about to provide, therefore, is only my own experience with the practice. But to me, the biggest difference that modeling provides to your science teaching practice, um, besides, of course, your school secretary complaining about how many whiteboard pens you burn through every school year, is the part where instead of introducing new ideas to the students with a lecture or a demonstration, we try to introduce students to new ideas through a hands-on laboratory activity. Um, this has like a whole suite of advantages. It provides a little bit of like, I guess, equity in the classroom. There used to be a bunch of lessons that I would approach where I would say, think about that time that you hit a baseball with a baseball bat to talk about momentum, not realizing that not all of the students in the classroom have had that experience of hitting a pitched baseball with a baseball bat. Um, so instead of relying on this schema that we can't actually guarantee, we can guarantee that when we get to the part of the lesson where we're talking to the kids about what the lesson is actually about, we can guarantee that they've all had a common hands-on experience upon which to base the discussion because we provided them this standardized hands-on experience. Um, the best way to get modeling instruction to get real good at it, there's no way other than by attending a summer session. They're available in lots of different places, and at the end of the slides, I'll have a link to the AMTA's website where they have all of the different places where you can attend a 2-week summer session. I'm currently working on setting one up in my area, which is in Los Angeles. It is not all put together, so if it's not a thing that's widely available for public enrollment this summer, then hopefully at the latest it'll be a thing that's available for public enrollment starting next summer. In the meantime, as you are deciding to um, attend one of these summer workshops or teach modeling or incorporate modeling into your practice. I hope that this lab that I'm about to go through and a little bit about the approach of modeling that it incorporates is something that you can try in your classroom. I'm hoping that you're attending this session before you were teaching momentum. And at the end of it, I'm going to be dropping a link to a Google Drive folder that has in it all of the resources from this talk that you need to try this laboratory in your classroom. Also, in a small way, this talk has been sponsored by Vernier, the science supply company. And so at the end of it, of the attendees who were here, minus a couple people who I know don't need it, a couple of my friends are attending. We'll be doing a raffle, and one lucky attendee will be emailed a $50 Vernier gift card afterwards, so that if you don't have all of the laboratory equipment to do this lab, hopefully you can purchase a nifty toy or two to help round out your physics teaching toolkit. That being said, this is introducing momentum with precision collisions. I think most physics teachers get to momentum sometime after forces. And usually physics teachers will start with a demonstration and then roll directly into some version of this lecture. I've seen lots of nifty demos for introducing momentum. I like stacking the tennis ball on top of a basketball, dropping the stack and having the tennis ball go way higher than it should be able to under simple conservation of energy. That's a classic. Or some really ambitious physics teachers sit down on a skateboard and grab a fire extinguisher, fire it one way, get going real fast in the other direction. All of that stuff is nifty, but we have research from the physics education research community that suggests that it's actually best to start with a lab and not a demo. A lot of teachers do the demo and then they talk through the fact that you got Newton's third law, you got Newton's second law. When two objects collide against each other, Newton's third law says that they're going to exert equal and opposite forces on each other. Newton's second law says that those forces are going to be equal to the mass of each object multiplied by the acceleration they experience. Acceleration is a change in velocity divided by time. You multiply both sides by time, swap the change in velocity for the definition of the change in velocity and distribute mass, and then move all of the initial and final velocities to the same side of the equation. And by doing some nifty algebra for the students, you end up with the conservation of momentum. I am not saying not to do this. This is real good. It's real good for the students to see equations derived, especially the students who go on later into physics and engineering, where most of the game is deriving equations and justifying them. What I'm saying with this approach is instead of starting with this, or instead of starting with a demonstration, if you have the equipment to deliver it, start by trying this lab instead. See if the kids can get to that conservation and momentum statement all on their own. Of course, there's trickery at play. We're basically doing magic. We're doing a trick, and then the reveal is the conservation of momentum. To get there on their own would take, thousands of years, the same way it took our species thousands of years. So here's how I try to guide the students there. In the lead up to this laboratory activity, I got a pre-lab, but it's not your standard pre-lab where the students read the procedure and the materials in advance. The problem with that is, like a magic trick, there are elements I'm trying to keep secret until the reveal. And so I got a couple videos that I recorded that I assign as homework on a Google form, and then we debrief them right before we start this lab. I got this first one, a little bit of an anchoring phenomena for the way that this set of lessons goes. I hop on my skateboard, and my campus security guard was kind enough to throw this little weighted beanbag at me. I catch it and I roll the other way. So in the homework, kids watch this short little video that I recorded, and then underneath it are a couple questions about the forces being applied. Normally students have a fine time with this. When I catch the beanbag, a force is applied on me, and that force that is applied on me is accelerating me. And then the part where in the student responses I get much wilder things are in the second part of this anchoring phenomenon. Campus security guard is not here. And then I hop onto skateboard with weighted beanbag. And I simply throw the beanbag away. And the act of throwing the beanbag away accelerates me in the opposite direction. I'm sure if you teach physics, if you've taught physics, you were keen to the fact that the kids get Newton's first law, they get Newton's second law, because that's the one that we're always asking them to use when it comes to answering homework questions, answering test questions. But the kids usually struggle conceptually with Newton's third law. You get all sorts of funky stuff. They're drawing the both forces of the force pair on the same object in a free body diagram. This is the phenomenon where in the pre-lab assignment, I get the most diverse, the most telling answers about student misconceptions. And then afterwards, the last question on that little pre-lab is I ask them, what's similar between these two and what's different between these two? And so in the build up to the lab, they usually get that the thing that's similar is the interaction of me with the beanbag causes me to move. And the difference is that in one of them, I'm catching the beanbag, and in the other one, the beanbag is being thrown. So the next day when they come in, I have all of the lab setups set up. Luckily, I have a TA every period. They're really instrumental in, keeping the class moving at the correct pace. We start with a discussion about this, and the challenge is, can we come up with a conceptual framework, an explanatory model that can contain both of these things that they saw the night before? Like, can you explain both of these things that happened using a singular set of ideas? This is a modification of a talk that I originally gave at USC last December. So my apologies for everybody who's in a region that doesn't use the NGSS standards. But just in case your admin asks, if you got one of those forms that you got to fill out with the lesson standards, in terms of the NGSS standard alignment, this one lines up perfectly. This is HS PS22. We're using mathematical models to support the claim that the total momentum of the system of an object is conserved when there is no net force on the system. That is contained within the disciplinary core ideas that are all about forces. So we start by using Newton's laws, and then we build up to the fact that momentum is defined for a particular frame of reference and is the mass times the velocity. The trick to this lab is that we're going to get to that definition, the fact that momentum is mass multiplied by velocity, by leaning on some cross-cutting concepts, the main one being patterns. This lab is going to use a pattern that the students have been aware of since late elementary school or early middle school, in order to get them to the idea that there's a thing called momentum and it is mass times velocity. There will also be a part where the students are aware that this event, a collision, has a effect where objects' velocities change, and that the cause of that is the collision itself. And we can encapsulate this cause and effect thing by using the momentum conservation equation that the kids invent. And if you are ambitious, you can also get the kids to realize that systems and system models, the idea that there are boundaries and limitations of this equation that we're going to cook up, you can also get them to realize that on their own during the debriefing discussion of this lab. If you are willing to sabotage one of the students' experimental setups, which is a tactic I've taken to in recent years. A little bit more on that later. This is a 3D lab. It hits on all of the parts of NGSS instruction that you would want it to hit on if that's a thing that you're implementing in your locality. In order to do precision collisions, you're definitely going to want some sort of crash cart. It doesn't matter which brand of crash cart you have, of course. For all of the slides that come after this, I'm going to be talking about the Vernier equipment because that's what I have in my classroom. They're the folks giving out the gift card. If you have other crash carts, if you have the Pasco set, that'll work just fine. All that you're going to need is you're going to need a motion track, 2 crash carts, and a way to measure the velocity of each cart. There's lots of different ways to do that. They have various advantages and disadvantages that I'll detail in the next couple slides. in case you're fortunate enough to be a chooser of your lab equipment, depending on what group you're teaching this to, I do have recommendations. So here on the left, I have the setup using vernier crash carts. We got an elastic collision, and this is using the current generation of GoDirect PhotoGate. The GoDirect PhotoGate are connected to one of the LabQuest 3 tablets, and the PhotoGates I really like for my standard physics classes because they are simple and they represent the data in a nice, clean way. They only capture the velocity of the cart as some element of the cart passes through the photo gate in question. In the setup that I have here on the left, each one of my carts has an aluminum rail sticking out on top of it. And so when the aluminum rail passes through the photo gate, the aluminum rail breaks the lasers in the photo gate and measures the velocity. It makes the representation of the data nice and clean for the kids. We have a blue dot before, that's one of the carts before they collide. We have a red dot before, that's the velocity of the other cart before the collision. And then afterwards, once they hit each other and bounce back in the opposite directions, we have a velocity for one cart and a velocity for the other cart after. Straightforwardly, we have our before and after velocities. Here on the right, I have the same two vernier crash carts with ultrasonic motion sensors. And then, to accommodate that, attached to the crash carts are these little plates that are designed to reflect back the ultrasonic sound that they emit in order to measure distance. We graph it down below, and we get a lot more data. We get both the position time graph of each cart, and then, of course, the LabQuest 3 is doing the calculus. It's taking the derivatives of the position graph to get the slopes. Those slopes are represented down before as the velocities. I do like this approach a lot more, but like I said, for my standard classes, I try to keep it strictly to the photo gates, just because the data is easier to see, easier to conceptualize. The only numbers that they need are the ones that are showing up there. To use the ultrasonic motion sensors, the kids need to have a lot more intuition about velocity time graphs and know exactly where they're looking, right in this region here where the velocities change for their collision. The other downside to using the ultrasonic motion sensors is that they have a directionality to them. They read positive as being towards the sensor and negative as being away from it. And since the two sensors are facing each other, their directionality is opposed. So here on this velocity graph, both of their velocities read as positive, and then after the collision, both of their velocities read as negative, even though these two carts were pushed towards each other. I've also tried hybrid setups, depending on how many kits, what equipment you have. You could also totally do a setup where you have one photo gate and one motion sensor. That also works fine. You just got to make sure that for the collisions where there's bounce back, that the cart that is being measured by the photo gate, that the kids are doing those collisions in such a way that it actually bounces back through the photo gate. If your lab equipment was ordered very recently and you were lucky enough to have the brand new Vernier GoDirect motion carts, this is the best way to do it if you have it. These carts are great because they don't need external sensors in order to measure the velocities of the carts. They have this nifty literal encoder wheel on the bottom, which is a wheel with a mirror on it, and the mirror has black stripes painted on it. There's a little laser in there that bounces off of that mirror. So based on how quickly the laser light is blinking, the cart knows how fast it's traveling. Each cart has a little rechargeable battery inside of it, so you have to charge them the night before. They connect to student Chromebooks via Bluetooth. So if you have this set, you don't also need the LabQuest 3 tablet. Kids just go to graphicalanalysis.app, and all of the data will be taken live on there. This is the same crash as the other two that I showed, except since with this, the directionality is determined by the carts. As long as the directional arrow on both carts points the same way, you will get true signs on your graph, positive and negative. So down here is the crash. We have the positive before velocity of the yellow cart. It was headed to the right. We have the negative before velocity of the green cart. It was headed into the left. They bump into each other, they bounce back, they head opposite directions. And so up here, we got that positive velocity on the green cart and that negative velocity on the yellow cart. This is my favorite way to do this when possible, especially for your AP groups, because a big part I find for AP is description, interpretation of graphs of motion. And I think showing the curved features on here is good at getting the students to understand that during the collision, the carts are accelerating, which is why we see curved features on the position time graph. Of course, if you don't have access to those crash carts, there are always simulations. This is a really good simulation of momentum and momentum collisions from O-Physics. It's always my go-to. It's a really good website. Only downside to this is that there's research about the fact that simulated labs aren't as rich as hands-on laboratory experiences. It is better than nothing, but if you have the crash carts, please take the time to set up, or ideally have your TA set up the crash carts so that they could do the labs live for real. The other part that makes the simulations not as ideal, in my opinion, is the part where you can't hide information from the students because it's usually just there on the web page. In all of the laboratory documentation that I'm going to provide in the chat after this, you'll notice that the word momentum, it doesn't appear anywhere in the laboratory documentation. The deal with that is this is supposed to be their introduction to the idea. And I always find that if there are key search terms in a lesson, the kids, when they have access to their Chromebooks, they will just go straight to Googling and it'll ruin the entire surprise. So whenever possible, whenever it's reasonable, I try to omit the most important search terms from the design of the lab. My AP kids just got through a circular motion lab, and the word centripetal appears nowhere in there. We're just spinning weights on strings like cowboys, and then afterwards we talk about what all of that meant. And then the word centripetal doesn't show up until well into lecture. Same deal with this. I recommend trying to avoid the word momentum for as long as possible, though I always find that in the lead up to this throughout the year, kids are aware of that word. They've heard it used in popular media. So when you get to lecture, you finally get to tell them, hey, there's that word that you've been using a little bit wrong all year. I know that you've been talking to me about momentum. You've been talking to your friends about momentum. This lab that we just finished, that's what momentum is actually about. So here's the important part. The trick to the precision collision lab is that for no reason whatsoever, we don't tell them why we're having them represent the data this way. We are having the kids represent the data in a very particular and finicky way. We're going to have the kids crash the carts into each other. And I got 8 different collisions that I recommend you do that lead to really good, rich scientific discourse about what the data means. But they're not just taking a data table in their laboratory notebook. We got posters or maybe whiteboards, or I also have included in the set of laboratory documentation a printable little PDF that you can print out and then put it in a sheet protector so that students can draw their rectangles right on top of the graph paper. The graph paper that I have in there is marked out with the correct axes so that these rectangles are as wide as the mass of the crash cart and as tall as the velocity. I'm sure all the physics folks in the audience are looking at this and being like, oh, actually, okay, yeah, that's neat. The 8 collisions that I have to walk them through this in a way that ends up being profitable later when you're guiding the students through scientific discussion are the following. Number 1, equal masses push together to bounce with one of them at rest. So one cart crashes into the other gets sent off, and the first one that was moving towards it comes to a nice clean rest. Number 2, different masses push together to bounce with equal velocity. So the 2 carts come together, bounce, and then head back in opposite directions. Equal masses push together, but to bounce with different velocities, with really no more instruction being given than that. I usually just tell them push one fast, one slow. Trial number 4, different masses push together to bounce with different velocities. And then after that, with trial number 5, we switch gear. Trial 5, equal mass, one is pushed at rest, and when they're pushed together, they stick together. For this bouncing and sticking, of course, you got lots of different ways that you can pull this off with your equipment. My favorite way is to do it with simple magnetic tabs, just so that when the lab starts, the tabs are set to repel, and then switching, you switch one of the magnets backwards so that then they stick. Of course, if you don't have magnetic tabs for your crash carts, the classic way to do this are crash carts typically have an integrated spring inside. So for these bouncy ones, you do that with the spring. And then when you switch it to stick together, you give them a little piece of Velcro so that the carts stick together with the Velcro. Trial 6, different masses pushed together to stick. Trial 7, equal masses, again, pushed together to stick. Same velocity, different velocity, doesn't matter. And then number 8 is the one that throws them for a loop and leads to a lot of rich discourse afterwards. Different mass with the tabs removed, and you preload one of the springs, put the carts together, and then press the mechanism on your crash carts that forces the two carts apart. The kids usually object to that one being in here because they don't get why an explosive collision would be included in this set. Again, for all the physics folks following along at home, this is designed so that trials 1 through 4 have some stuff in common. 1 through 4 are all different elastic collisions, while trials 5 through 8 are all of the various types of inelastic collisions. I got a couple samples of student work here to show you. This is one of my favorite student samples. This one includes really important error. And after I had a year where students made this error, and then I realized what was going on, I was like, oh, that's great. That's actually so good that in the future, I'm going to sabotage one of my 7 groups so that this error happens every time. For this one, you'll notice that the areas on each side are not the same. The areas on the right are actually a lot bigger. And then I realized that that was due to the fact that the student's cart, the track was crooked. They didn't follow instruction 1 of the lab and make sure that their track was level. And I realized that for all of their trials, the area for the post-collision side was too big in the positive direction. So I was like, wait a minute, I think your track is tilted to the right. And then I went over to their track and I put a marble on it, and the marble rolled downhill to the right. So now when I do this, I either just straight up sabotage one of my 8 groups, or for the AP group. They don't like that. So I actually warn them in advance and I tell them that your setup is different so that we can talk about the difference between your setup and the other 7 after the lab. It's one of those good experiences for the students, both so that they can appreciate the importance of setup, calibration, making sure that all of the external influences for a lab that's supposed to produce a certain type of data are removed. And also to let them know that the nature of the data is what allows us to then assess the type of error that's present here. Is it random error? Is it systematic error? So that you don't get students, I don't know, measuring gravity is 9.9 and then saying that that 9.9 measurement is due to air resistance. Here's another good example, and this one is just spotless top to bottom. Big fan of this one. Real nice because they also color coded it. I recommend having them color code the rectangles as the colors of the carts themselves. Just makes it real visual. And this group just did an excellent job showing off exactly what we're trying to get out of these rectangles. Their version here of number 8 is really good. Big fan here. This rectangle on the left for trial number 8, and just so you know, this is the one where the 2 carts explode apart. Before on the left-hand side, there are no rectangles. And then afterwards, on the right-hand side, we have a rectangle which is almost 0.4 meters per second tall and about 300 grams wide. And then down here, we have a rectangle which is too tall and about, I know that that looks like a 7. It's actually 580. It's just they traced it funky with a pen. So this is about 600 wide and about 2 tall for a total area of 12. This one is about 3 wide with a height of 4 for a total area of about also 12. And so on the left-hand side, we have no total area. And then on the right-hand side, we have an area of about positive 12 and about negative 12 for a total area of 0. If you know the physics of momentum and you kind of get what I'm getting at with this lab, then the whole point of it is for the students to set up these posters. And then afterwards, the way that this looks in my class, oh, I just realized the people in the stock image are drinking beer. The kids are not drinking beer when they do this debrief, obviously. But the whole point of this lesson is to get them to make these posters during a long form block period. It takes about 90 minutes to get good data for all 8 trials. And then on a subsequent class, bust out the posters and then lead them through a discussion about what they see. The discussion strongly uses the students' pattern recognition in order to get them to recognize that for all of these, the total area of the rectangles is almost the same before and after. Of course, it's not perfect. There's a little bit of friction. The tracks might be a little bit crooked. You might have to do a little bit of estimation to push them there. But students should be able to realize that the total area before and after are the same. This is supported in the lab itself in its design. Trial 1 and 8 are kind of the bread of the sandwich of the 8 trials, because those are the 2 where you can point the students' eyes in order to get them to the idea that the total area is the same, and that if they were to check that mathematically for the 6 trials in the middle, for the ones where it might be harder to see, it should still be confirmed. Just a reminder, that first trial was that one cart is at rest and then the other one bumps into it, transferring all of its momentum to the other cart. And then that first cart that you push towards it comes to rest. For that one, the rectangular map looks like a rectangle and no rectangle. And then afterwards, no rectangle and a rectangle of the same area. 0 plus number is equal to number plus 0. And then for trial 8, they get another version of this that pushes them towards the idea that areas above the axis are positive, areas below the axis are negative, and those areas are capable of canceling each other out. That's why for that 8th trial, we got the explosive collision with the preloaded spring, so that they can clearly see that before this one, there's no areas, and then afterwards, they're equal and opposite areas. Before the discussion, just to prime this, it's nice to go around and check in with each one of your groups one by one once they've produced their poster of data, and ask them if they can see what's common between 1 and 8. And then later on, when you're leading a larger discussion, either with the entire class, or sometimes it's too much to do that, and I like to split my class in half and have a small discussion on one half of the class with 4 of my groups, and then have that same discussion on the other half of the class with my other 4 groups. You can get them to agree that this is the pattern that they see amongst all of the posters, and then they can confirm this mathematically once they have arrived at that initial pattern. I know that lots of teachers of physics, some of us do energy before momentum, some of us do momentum before energy. Sometimes we disagree with the way that it is in our textbooks and we just end up doing our own thing. That's me. I teach energy before momentum, even though our district's curriculum says to do momentum before energy. I just like energy before momentum, so that we can get the one that's mathematically more difficult out of the way first. And so that I don't have to do that thing where you teach about momentum and collisions, and then after energy, you have to circle back to elastic collisions and teach them that energy is conserved there. You can absolutely do that. Don't get me wrong. Nothing wrong with it, just a personal preference. In the lab documentation that I'm going to link in the chat, in the version of the lab document that I made, all of the statements in there about energy are bolded, so that if you teach energy after momentum, you can remove all of the questions and all of the comments in there about energy when you're doing this laboratory activity with your students. But after the initial discussion is done, I ask the students to calculate kinetic energy for each cart in each trial. For groups where I know that the students struggle with math, which is a common thing these days, and just also special case. I'm in a district where physics is a graduation requirement. It's fabulous. I love it. I love getting to teach everybody the physics, but this means that there is no like hard and fast math prerequisite before they come in. I found it's very profitable to make a spreadsheet where they basically just type in the masses and the velocities, and then it calculates the 1/2 mv squared for each trial for them. This is why the 8 trials are kind of sorted out the way that they are. Those first 4 are elastic collisions, where, for important reasons, energy is conserved. So for those, the energy will add up before and after. And then the last 4 are inelastic collisions. So when they do those energy collisions, those collisions, the energy does not add up before and after. And again, you could have conversations with them, important reasons why the energy doesn't add up. Along with the laboratory documentation that's in the Google Drive folder that I'll link after this talk is done, are some, I guess, teacher notes, just some hot pro tips about things to say to the students to get them to understand what you want them to get out of this laboratory activity, how to guide the discussion. They can usually really easily latch on to trial number 8. Again, that's the explosive collision where the 2 carts are driven apart by that spring. Almost all of the students latch on to the fact there that the energy came from the spring, not from the motion of the carts. And that is a type of potential energy that they put into the cart when they took their little thumb and they pushed down the spring plunger. The other reason why I prefer using the magnetic tabs to make them repel and attract when they collide into each other is that it produces a much more dramatic sound during the laboratory activity. When the magnetic tabs are used to make the carts have elastic collisions where they bump into each other and then repel, it's dead silent. It's great. There's no sound at all. Unlike when you use the spring, you can hear the sound of the spring colliding into the other cart and you get that satisfying little ping. Same when you're doing the inelastic collisions. I prefer the magnetic tabs to using Velcro because I feel Velcro's real quiet, but with the magnetic tabs pulling the carts into each other, you get that nice loud crash. The absence of sound in the elastic collisions and the presence of sound in the inelastic collisions, I find is really profitable to lean on when you're leading the class through the discussion about why energy is not conserved during the inelastic collisions, but it is conserved during the elastic collisions. The kids seem to have a good intuitive understanding that sound carries away energy from the system. So in the collisions where there is no sound, all the energy stays there. But in the collisions where there's a loud sound, that bang, that crash, it helps with their intuition about energy leaving the system. Like I said, we're not always, straight up doing science. A big part of doing the science education is doing a magic trick where the reveal at the end of it just happens to teach the kids the correct lesson. Um, like I mentioned, this leans on their pattern recognition. Um, if you are teaching this after energy, which means you get to do the debrief with this energy discussion, it's nice to have them notice that in the energy calculations, they are also there detecting patterns. They just don't happen to be built directly on top of geometry. They have a really hard time explaining this in the later 4. So you might have to explicitly tell them, no, it is okay that energy does not add up in collisions 5 through 8, and then talk them through the whole sound thing. And then if you are doing this with energy calculations, it's nice to talk about the segregation of the 2 categories, trials 1 through 4 being elastic, trials 5 through 8 being inelastic. Again, these categories not just arising from the fact that they bump into each other and they bounce, or they bump into each other and stick, but the fact that these categories actually emerge from the numbers that we get when we calculate the kinetic energies of the carts before and after each collision. Sticking to the theme of NGSS alignment, it's nice to do a phenomena-based assessment. So when I do the end of chapter test for momentum, we do this lab, and then I do that direct lecture I mentioned at the top, where we use Newton's laws to show them that correctly having control of Newton's laws allows you to derive other relationships, other things like conservation of momentum. We got this cool video from Richard Garriott, which is on um, I don't think it's on NASA. I think it's on the Canadian Space Agency's YouTube channel, where he shows elastic collision of two tennis balls in space. And for this question, I show the kids this little video on Google Form. It loops. And then I have them draw the same rectangular representations for the two little crashes that he does there. And I ask about, why is it important that it's in space? And then, you could cook up whatever numbers you want in order to have them do the assessment. If you are interested in trying modeling, I guess that's why you signed up, to give me a little bit of time on your Monday of your well-earned Thanksgiving break. I hope that you are able to try this lab. Give it a shot when you get to momentum, wherever that is in your particular sequence, and do rely on the method. Try not to do too much explaining. Just have the kids try doing these 8 different activities. Try having them represent the outcome of the 8 laboratory activities just by drawing rectangles. And then by talking the kids through it, having them figure out what patterns they see amongst the rectangles for themselves. Hopefully they can figure out that MV plus MV equals MV plus MV before we insist on tying it to, a deeper understanding of Newton's laws. If you give this a shot and it works out great, hopefully you can check out the American Modeling Teacher Association's website to see if there are available modeling workshops in your area. They're in a couple different regions all around the country, and if you stay updated on that page, hopefully this summer, or at the latest next summer, I'll be able to offer a 2-week modeling workshop in the greater Los Angeles area, since we haven't really offered a workshop in SoCal in a little bit now. For contact information about the American Modeling Teachers Association, all of the various social media contacts are here. They're on Facebook, X, LinkedIn, YouTube, Instagram, Discord. I'm also on LinkedIn. You can find Eric Robinson on LinkedIn. You just type in Eric Robinson and it looks like me. That would be a way to find me. And the Discord is actually really great. If you're on Discord, you can hop on there, and there's a bunch of different channels based on what subject you teach, what level you teach. There's even like spun out sections amongst the physics crowd of like, are you teaching physics first in 9th grade? Are you teaching on level physics in 11th grade? Are you teaching AP physics? Because all of those things are modeled, and all of those things are so different that they have to be modeled in slightly different ways. If you hop on the Discord, I'm also there. And if you ever need resources, I'd be glad to provide them. Or if you want to share your resources and ask for feedback, always glad to do that, especially to new modelers who are like, I'm new to modeling. I made this modeling thing. Is this modeling? Love having those conversations. The AMTA also has a monthly podcast called Science Modeling Talks. It is like a monthly PD, but unlike the PD that your admin probably give you, you will enjoy this one. It's really good, interesting speakers, interesting stories, useful stuff. And in a lot of cases, some of it is directly applicable in your classroom. Like I have gotten Socratic dialogue tips that I was able to use directly from the podcast, riding my bike to work. I was like, oh, that's a great idea. I am going to use that today when I am debriefing energy stations. Be sure to check out the website, modelinginstruction.org. Members can log in, get all sorts of instructional resources, tests, quizzes, homework. And crucially, if you check out the workshops in your area, you can see what workshops are available in your area this summer. You could always, if you'd like to, email me directly at erobinson@gusd.net. That's my work email there, in case you have any questions about this particular laboratory activity. Or, if you try it and it goes great, or if it doesn't go great, you want to give me feedback, I'd love to hear that as well. And then for this talk, there is a survey, if you have time, to scan that QR code and answer a couple questions, if you'd be so kind. about the talk, about how it went, or any questions you would have about follow-up. Let me hop on in the chat real quick because I promised I would add a link to a Google Drive folder that contained all of the files that you need for this. And then on the topic of looking at the chat, if you have any questions about this laboratory activity or modeling approach in general, all of that is stuff I'd be glad to answer. So in here, I got some different stuff for you. I have, oh, great. Glad to hear. Uh, 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 Glad to hear that this is timely for some of y'all out there. Oh, especially somebody starting it right after Thanksgiving. That is perfect. In the folder, Google Drive folder I just linked, I got a good work sample, of course, with student names removed in case anybody from my district is watching. That's just like the ideal version of what you would like your students to try and produce. There's a link to a really good resource from the Exploratorium, this science museum that we have out here in California, that is all about scientific discourse. Like, how do you get the students to talk science in the classroom? It's really good and it has pointers in there. It has a list of both teacher moves, like what are things you can do to induce productive scientific discourse. And then also print out in there for a list of student moves where if you ask a student a question and they like just don't know how to respond, they don't know how to even start the sentence. The student handout is really useful to leave a copy at each group so that if they get stuck, they can literally just pick from a menu of sentences to start their response if they're having an issue with the questioning. There's also a copy of the slide deck in case there's anything from here that you'd like to reference, including a link to the O-Physics simulator that simulates the collisions, and a link to the article that I mentioned where we've researched like are virtual labs as good as hands-on labs. The answer is no, hands-on labs are irreplaceable. All that stuff is on there as well. And then in that folder, there's also a PDF of a printout. It'll just print out like 8.5 by 11, and it's an insert to go into a sheet protector so that the students can just whiteboard directly over it if they're having a hard time doing the rectangular representations. I've had groups where they struggle. So what I've found is really useful is to give them a straightforward situation. I use that video of me on the skateboard and I make sure that everybody's drawing the rectangles correctly for that scenario. Where if it's me throwing the beanbag away, there should be nothing on the left, and then on the right, me is a really wide, large mass rectangle that's very short because I'm slow, and then next to that is a very tall but very skinny rectangle for the beanbag because it's fast but not very massive. I think doing one of them with the kids, just as an example, before they get into the lab, real useful for making sure that they're not drawing the rectangles in a way that's not productive later when you're doing discussion. Also in there are a couple teacher notes just about my thoughts of this particular lab, stuff that'll make implementing it a little smoother, stuff that I mentioned before, like maybe considering how to identify a crooked motion track, how to see that in the data, and then how to show to the kids that their track is crooked and that this is affecting their data, along with a little bit of other advice, just small things to make sure that this goes over smooth. Are there any questions in the chat about this particular, like this specific activity, or I guess like the modeling approach in general? No? Okay. Like I mentioned, thanks everybody for coming out. I hope you all have a lovely Thanksgiving and a lovely Thanksgiving break. And as I mentioned, a lucky attendee after this, be sure to check your emails, the ones that you use for registration. One lucky attendee will be receiving a $50 Vernier gift card in their email to help round out their physics teaching toolkit. Yes, me as well. I would also love to see a modeling instruction workshop in SoCal. As it is right now, I've been at the high school I'm at for about 3 years, and at this point, we have all of the science teachers at our department modeling. Everybody loves it, works real well. The kids are having a good time. Admin loves it because standardized test scores are up. It's